Welcome back, guys. So here is your next video for the week. Before we started on and jumping in with covalent bonding, I also wanted to go over things every now and then, things that you guys are doing well, things that I'm really proud of, and also going over answers for different assignments throughout the week, so you guys can be checking those. Again, I'm trying to give grace. So if you made a mistake or you didn't submit something correctly, just shoot me an email, and I am more than happy to help you out, to walk through that process and all of that good stuff, especially if you have missings. I know some of you guys are starting to get those back. Just let me know and we can take care of those. If you're having trouble with technology, I completely understand. I'm having my fair share of technology issues. For those of you guys that watched the saga unfold from the last video where 4 minutes of audio just disappeared out into the unknown. Oh gosh, now I'm starting to think of the Frozen song in my head. Bad choice of words. So let's just get started with the next thing. So first thing I want to do is I want to recognize someone who did a really, really good job with the extra credit challenge, because they found their own challenge, which was kind of cool. What they did is they basically froze stuff in ice. Here we go. And used salt to basically to melt the ice. And this is something that we actually use and we see in the real world. So this person will get the Smarty as well, even though there's going to be 2 Smarty winners in this class. So congratulations, Sadie. But basically what you did is she demonstrated that salt lowers the freezing point, okay, of water. Because the way that salt interacts with water is actually really, really interesting, and it has to do with how ions work. So we talked about how salt is made up of 2 ions. It's made up of a cation of sodium, and it is made up of an anion of chlorine. So together, they stick together in the form of salt, and they form this solid. However, in the presence of water, they get separated out into 2 individual atoms floating around. So this is actually what people do in the winter up north. They will sprinkle salt on frozen driveways and things like that, and it will actually melt the water, melt the ice, because it changes the freezing point. The freezing point actually gets lower than what it typically is. And normally water's freezing point is about 0 degrees Celsius, which is about 32 degrees Fahrenheit. I wish it was a little bit colder here. But anyways, so they did this, they sprinkled salt on top, and then they basically watched it melt into this cool formation, and you were able to get the shells out that were frozen. It was really cool. So congratulations, Sadie. I wanted to highlight that, especially as we're talking about salt. I'll continue to highlight other things as well. Speaking of which, let's go through the Nearpod you guys did yesterday. I'm picking out some of my favorite answers and responses to those questions. So let's go over the Lewis dot diagrams before we get too much further. If you feel like you already have a handle on this, you can always skip forward. But I would make sure that you understand it before we move on to the next concept. So the first question on the Nearpod was to draw a Lewis diagram for a neutral carbon atom. So we had to have a periodic table, or if you already know this stuff, that is great. But if you are looking at your periodic table, carbon is going to be right here and has an atomic number of 6, but we know that not all of those are going to be valence electrons. The number of valence electrons for carbon is 1, 2, 3, 4. So this would be an acceptable answer. I took this from the Nearpod. Somebody's drawing here. So good job, person. This is correct. Most of you guys got these first couple correct. All right, number 2. So number 2 was similar. Again, you're just drawing a neutral atom, so you're not drawing ions at this point. So what you should have done is find sodium, which was over here. I circled it there on the periodic table. So neutral sodium atom has no charge. You only have 1 valence electron because, which is why it's going to form a cation most likely, because it's on the end there. Cool? All right, then let's move on to the 3 other ones, which were a little bit trickier. All right, I'm putting 3 and 4 on pretty much the same section because you solve them the same way. The way that you solve these ones is you basically have to create an ionic compound. So let's start with the first one. These are both the correct answers of what you should get at the end of the day. So good job if you got this, but here's lithium, and we had chlorine right there. So what you're gonna do, lithium has how many valence electrons? It has 1. And chlorine has 7. So it only needs 1 more to get that full octet that it's looking for. So what's going to happen is this 1 valence electron is going to, and some of you guys actually showed this with the arrows, and that is fine as well. Those are both of those atoms neutral. So what's going to happen here is this electron right there is going to move over here to the chlorine, which is why when you get the end result, you have a full octet on the outside of chlorine, and you don't have any electrons, any valence electrons, keep in mind, on the outside of lithium. So you have a positive cation for lithium and a negative anion for chlorine. You do the same exact thing for this second combination. The second combination, you can see you have potassium, which is over here, and you have bromine, which is right here. Same thing. Potassium has 1 valence electron, whereas bromine has 7. So the exact same interaction is happening there. Potassium is losing an electron to make it positive, and then bromine is taking that. So that's how you solve 3 and 4. Let's do number 5, and then we will be good with this. Okay, finally we have magnesium and oxygen, which is a weird combination because notice we are getting a little bit more complicated here. So magnesium, if you look at your periodic table, is going to be right there. And then you have oxygen, which is over on the other side. Now let's look at the valence electrons for each. So valence electrons for magnesium is going to be 2, oxygen is going to be 6. So if we were to draw this out, and this is the neutral one, not the ions, we would draw it something like this. We would have 1, 2, and let me erase that little stray marking right there so that we're not confused. That's not an electron, that's just a mistake. That's what we call that. All right, so then the neutral state of oxygen is going to be 1, 2, 3, 4, 5, 6. So you have 6 valence electrons on oxygen, and it wants to have a happy octet. Magnesium also wants that. So what is going to happen here is magnesium, instead of losing 1 electron for a charge of +1, you're actually going to lose both of those electrons. So this guy and this guy are both going to get transferred over here. They're going to go here, and they're going to go here, and the end result is going to be what you see there. Okay, so you're going to see magnesium with a +2, and you're going to see oxygen -2. So good job, people. I'll keep highlighting the correct answers, and let's move on to talk about covalent bonds. Whoop. Okay, so last time we were talking, when I introduced ionic bonds, basically bonds, and what we're talking about right now, we're talking about something in particular. We're talking about intramolecular bonds. In case you guys are just ahead of the game and thinking about other types of bonds, we're only talking about bonds that exist within one molecule. There are other kinds of bonds out there once you start talking about molecules interacting with other molecules, but we're talking about molecules. Molecules are going to be when you have atoms that are sticking together some way or another. So there are 3 ways that we can have this happen. We can have our ionic bonds, which we talked about before. So you have a positive and you have a negative charge that are being attracted to each other. These are really strong. It usually takes a good amount of energy to get those apart because they're kind of like magnets, right? Magnets work under the same kind of principle. Today we're going to talk about covalent bonds. We're not going to spend much time on metallic bonds, but know that they exist. They are out there. But covalent bonds are what we're going to spend some time on today and probably a little bit next week as well. Covalent bonds are going to be shared electrons. Okay, so shared electrons are going to happen between a lot of different elements, particularly ones that are close together on the periodic table or ones that are not likely to form ionic bonds. We see this fairly often, and if you even want to get more specific, there's actually different types of covalent bonds, which honors we will talk about a little bit more in detail as well. So let's go ahead and let me kind of erase this. Okay, so covalent bonds, let's get a quick definition up here for you so that you guys that are taking notes, you guys can have this as a general idea of what's happening here. Covalent bonds, again, are going to be when electrons, let's say, actually, let me get a little bit more specific here, occur when one or more pairs of electrons are shared between two atoms. So let me give you an example here. Let me put my periodic table up here so you guys can follow along with me and so you can kind of see what's going on. So here's my periodic table right here. So let's start with chlorine. So let's say that I just have a lonely chlorine atom and no little sodium cations to be with it. Sad. So chlorine is going to be over there and it's going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. So if I draw my Lewis dot diagram, I have 1, 2, 3, 4, 5, 6, 7. It is so close to getting that last electron, and it's going to be extra needy because it wants a full octet. Now let's say that we're in an environment where we run across another chlorine atom. 1, 2, 3, 4, 5, 6, 7. That one is also needy and also needs to fill that last kind of pair. So what they're gonna do, notice he's like, hey, I have one extra that's kind of lonely. This guy's like, I got one extra that's kind of lonely. What they're gonna do is they're actually going to share. So you're gonna get something like this. 2, 3, 4, 5, 6. In the middle here, we're gonna come together and form a molecule. Yay! Now we are all happy here. This pair of electrons is getting shared between those two atoms. Now, the way that we shorthand this when you're drawing your Lewis dot diagrams is you're not actually going to draw the two dots in the middle usually. You can for now as practice, but the way that you should actually write this is going to be as a line. That's how we show our shared pair. So each line represents one pair of shared electrons. Now both of these chlorines are happy. Those aren't electrons. Those are just smiley faces. So we are sharing our electrons there between those two atoms. Yay. And it's going to cause them to be kind of stick together, and it's also going to need some energy if you want to break this bond ever. So it's going to stay like that. Okay, so let's go ahead and do a couple more, and also I want to talk about how we show this, how we write these molecules out. So let's do methane really quickly. So methane is going to be one carbon atom bonded to 4 hydrogen atoms. Now, I don't have my periodic table up here, but I'm gonna just kind of ask that you trust me here, and hopefully you guys know. So hydrogen only has 1 valence electron, so it's going to look something like this, okay? And then carbon is going to have 4 valence electrons, so it is going to look something like this. And this is part of the reason why carbon is so vital for life, why we find it in every single living thing, and why it makes up sugars, it makes up DNA, it makes up amino acids. All of these things have to do with the way that it can interact with all of these different atoms. Now notice, carbon is kind of in an interesting spot because it's like it needs 4 more to be a full octet, which means carbon can be super friendly with our other atoms. So what's going to happen here is with methane, we are going to see that you're going to have 4 little hydrogens here, and they're all going to share their electron with carbon. So they're all this kind of happy little, I don't know what the proper term is now anymore. I don't know, happy little friend group. You guys say friend group, which I find weird. But happy little group. So you can have something like this, and that is actually methane. Now, there's a way that you actually show this when you're writing molecules out that is shorter. So we call this methane. Let me write that. Okay. But we can also say what is going on here by doing this, CH4. And so you'll see this in your book, and you'll see this, we'll practice with this a little bit more, but basically when you see a formula like this, it's actually telling you what kind of atoms are in bonds with each other. So that is telling you that you have one carbon atom, one carbon, and you have 4 hydrogens. Let's practice that for a second, because you're gonna have to do this on one of the assignments later, reading these formulas and being able to tell what's going on. So let me give you another one. Okay, so these are some different molecules that we're gonna draw the molecular formula. That's what we call that, what we just did on the last slide, where you see how many atoms of each are going to be in that. So for example, for propane, we're gonna have C3H8. So that means that we have 3 carbons, okay, bonded to 8 hydrogens. So it's basically kind of like a recipe for what is in that molecule itself. Let's do water. You guys probably already know what water is. It is H2O, okay? So that means that you have 1 oxygen and you have 2 hydrogens, right? All right, finally, let's do our last 2. Glucose, the formula for glucose is gonna be C6H12O6. So that means that I have 6 carbons, I have 12 hydrogens, and I have 6 oxygens, okay? Then finally, I'm gonna do caffeine. I'm gonna make sure I get this right. I always mess this one up a little bit. So C8, I'm sorry. See, I'm messing up already. C8, H10, N4O2. So caffeine, that is the molecular formula for it. It would be 8 carbons, okay? 10 hydrogens, 4 nitrogens, and 2 oxygen. Okay, so that's basically what those are. That's how you read those and decode those. And I think that's gonna be all I'm adding for today. So let me pause it, and so that's it for today, guys. I hope you guys learned something. Feel free to, again, rewind, rewatch, and take notes on whatever you don't understand. Email me if you have questions, comments, or concerns. I'm more than happy to help. Other things that are just whatever, just email me. I'm happy to help. I'm usually pretty quick. If you don't hear from me, just email me again. Just don't worry about bothering me. I will respond. So yeah, that's pretty much it. Miss you guys again. Good to hear from you guys virtually, and good to see some of you guys on Zoom. And I will see you guys soon. All right, bye.